You know all those apps on your phone? The ones that just work? They feel so simple, so effortless. But have you ever stopped to think about how they're actually made? It's not magic. It's this hidden world of problem solving and structure. Today, we're going to pull back the curtain and take a journey from pure chaos to clean, working code.
Right? It always starts with just a little spark, an idea. But how in the world does that tiny spark turn into something that millions or even billions of people use every day? Well, it's not luck and it's not magic. It's a discipline. And it's called software engineering. So here's the thing. The very first challenge, the biggest one really, has nothing to do with writing code. Not a single line. It's about taking that messy, abstract idea and hammering it into an orderly, concrete plan. This is where the real engineering actually begins.
Now, the key phrase on this slide is all aspects of software production. And that's absolutely crucial, because software engineering isn't just the fun part of typing out code. No, it's the whole shebang, from that first what-if conversation all the way to supporting and updating that app years after it's been launched.
And this slide just nails the core problem, doesn't it? A user says, hey, I want a simple app to share photos. But to an engineer, that simple idea just explodes into a whole universe of questions. How are we going to store the data? How do we keep it secure? What happens when a million people try to use it at the same time? Bridging this enormous gap, well, that's the entire point of software engineering.
So how do you even start to bridge a gap that big? Well, you don't just grab a hammer and start building. You wouldn't do that with a house, right? Of course not. You need a blueprint. You need a super detailed plan before anyone writes a single line of code.
And that blueprint, it starts with a skill that is so underrated in the tech world, just listening. Before an engineer can solve any problem, they have to deeply understand it from the user's point of view. It's all about figuring out the what and the why long before you even dare to think about the how.
And all of that listening, all those conversations, they get boiled down into this critical document, the Software Requirements Specification, or SRS. You should think of this as the official contract between the idea and the final product. It is the blueprint. It's what ensures that everybody on the team is building the exact same house.
And we are not talking about some vague, fluffy mission statement here. Oh no. An SRS is incredibly detailed. It defines the exact scope, every single feature, and even stuff you might not think about, like how fast it needs to be or how secure it has to be. It's designed to be exhaustive for a very good reason.
Okay, so you've got the blueprint, the SRS. Now you need a master plan for the actual construction. In the software world, we call this the Software Development Lifecycle, or SDLC. It's basically the high-level strategy for how you're going to turn that blueprint into a real working thing.
And here's the interesting part. There's no single best way to do it. The master plan you pick is a massive strategic decision. I mean, are you building a simple little website, or are you building the navigation system for a rocket to Mars? The plan has to fit the project.
One of the oldest plans in the book is the waterfall model. It's totally linear. You figure out all the requirements first. Then you do all the design. Then you do all the coding. You have to finish each phase 100% before you can even think about starting the next one. It's rigid, kind of like building a skyscraper floor by floor. And it's great for projects where you know exactly what you need from day one. But if things might change, this model can lead to huge delays and budget nightmares.
But what if you're not totally sure what the user wants? That's where something like the prototype model is a lifesaver. Instead of that rigid plan, you quickly build a rough working version, a prototype, and you get it in front of users right away. They give you feedback, you tweak it, and you repeat that cycle. This simple process can save a company millions by preventing them from building a perfect, polished product that nobody actually wanted.
Then you've got the heavy hitter, the spiral model. This is for the massive, high-stakes projects. Every single loop of that spiral you see is like a mini project that always starts with risk analysis. The whole goal is to find and kill the biggest, scariest problems first. This makes it perfect for things like aerospace software or medical devices, where even one tiny bug could be, well, catastrophic. So, as you can see, it's all about picking the right tool for the job. If your requirements are set in stone and aren't going to change, Waterfall is a solid choice. If you need a ton of user feedback to even figure out what you're building, prototyping is your best friend. And for those giant, high-risk projects where failure is just not an option, you bring in the spiral model.
All right, we've got the blueprint, we've got a master construction plan. Now we have to think about the internal structure. How the code itself is organized is just as important as what it does. We're not just building a shack, we're designing a digital fortress.
Something strong, stable, and easy to maintain down the line.
Look, any piece of software can work perfectly, for a little while. But if it's a mess on the inside, a poorly structured tangle of code, it becomes an absolute nightmare to update or fix later. Good internal design is what separates a reliable product from a fragile one. And two big principles guide this process: coupling and cohesion.
Okay, first up is coupling. This is basically a measure of how tangled up all the different parts of your code are. And the goal here is always low coupling. You want every piece, every module to be as independent as possible. That way, when you make a change to one part, you don't accidentally break something totally unrelated somewhere else.
Now, I know this slide looks a little technical, but you don't even need to read the words to get it. Just look at the pictures. The one on the left, strongly coupled, that's a tangled mess. It just feels fragile, right? The one on the right, uncoupled, is like clean, organized wiring. Each part is doing its own thing, making the whole system way more robust and easier to work on.
Now, the other side of that coin is cohesion. If coupling is about the connections between different modules, cohesion is all about what's going on inside one single module. And here, the goal is the exact opposite. You want high cohesion. This means each module should have one, and only one, well-defined job. Your user profile module should only handle user profile stuff, not a random mix of image processing and payment logic. It's like having a well-organized kitchen. All your baking tools are in one drawer.
So, from a chaotic idea all the way to a well-structured system, we've seen this hidden discipline at work. So, after all of that, what's the main takeaway? What's the one thing to remember?
It's this simple truth: the reliable, amazing apps we use every single day are not an accident. They are the direct result of a disciplined, thoughtful engineering process that takes chaos and forges it into something stable, useful, and built to last.
And really, it all comes down to that classic saying, if you fail to plan, you plan to fail. It perfectly captures the soul of software engineering. Just winging it leads to disaster. All that planning, that requirement gathering, and that careful design we talked about, they're not just optional steps. They are the absolute foundation of all great software.
So I'll leave you with this final thought. The principles we've gone over today are the bedrock of the digital world we live in. But as we start building even more complex things, smarter AI, truly immersive virtual worlds, how are these blueprints going to have to change? What new challenges will the software engineers of tomorrow have to solve?